Dear learners, in this e-content, we will discuss the calculation of work, heat, change in the internal energy, and change in the enthalpy for an adiabatic reversible expansion of an ideal gas. Before solving the problem, let me quickly recall the basic concepts involved. First, the system we are dealing with is an ideal gas. A gas is called ideal when it obeys the fundamental gaseous laws, that is Boyle's law, Charles' law, and Avogadro's law. It also follows the ideal gas equation PV is equal to nRT. It also satisfies the postulates of the kinetic theory of gases. Second, the term expansion means that the volume of the gas increases during the process. Third, the condition is adiabatic, which means that there is no exchange of heat from system to surrounding and vice versa, that is the surroundings to the system. Even though temperature is changed, the heat does not change. Finally, the process is reversible. This means it is carried out very slowly under controlled conditions and requires a driving force. That is, it is a non-spontaneous process. Now, based on these facts, let us calculate the parameters one by one. First one, calculation of Q. In an adiabatic process, heat is not exchanged between the system and the surroundings. That is, Q is equal to 0. This is equation number 1. And then calculation of delta E, that is change in the internal energy. We know that according to first law of thermodynamics, the mathematical formulation is delta E is equal to Q minus W. We know that for an adiabatic condition, Q is equal to 0. Therefore, substitute the value in the above equation. We get delta E is equal to 0 minus W, or delta E is equal to minus W. We know that heat capacity at constant volume is equal to the rate of change of internal energy with temperature at constant volume. This is equation number 4. Rearrange the above equation, we get dE is equal to CV dt. This is equation number 5. For the specific change of state, dE is equal to CV dt. That is integration of the above equation. We get E2 minus E1 is equal to CV T2 minus T1. Finally, we get delta E is equal to heat capacity at constant volume is multiplied by change in temperature. This is equation number 7. Third one, calculation of delta H, that is change in the enthalpy. We know that heat capacity at constant pressure, that is represented by Cp, is equal to the rate of change of enthalpy with the temperature at constant pressure. This is equation number 8. Rearrange the above equation number 8. We get dH is equal to Cp, that is heat capacity at constant pressure, dt. This is equation number 9. For the specific change of the state, that is the above equation may written like this with appropriate limit. Finally, we got delta H is equal to Cp T2 minus T1. This is equation number 11. Fourth one, calculation of W. According to first law of thermodynamics, delta E is equal to Q minus W. We know that for an adiabatic condition, Q is equal to 0. Therefore, the above equation may written like this: W is equal to minus delta E. Here we have to substitute the meaning of W. W is equal to minus CV T2 minus T1, because we know that delta E is equal to CV, that is heat capacity at constant volume, into change in temperature. This is the equation number 12. Now, work in terms of pressure and volume. Here the equation contains temperature. Already we know that temperature, pressure, volume, all are natural variables or global variables. Therefore, the above equation may also modify like this using the knowing items. We know that the basic ideal gas equation, that is PV is equal to RT. This is equation number 13. Rearrange the above equation number 13. Finally, we get T is equal to PV divided by R. Similarly, T1 is equal to P1 V1 divided by R. T2 is equal to P2 V2 divided by R. We know that temperature, volume, pressure, all are state functions. Therefore, we have to extract the definite meaning in between the two definite stages. Therefore, the above equation may written like this: W is equal to minus CV, that is heat capacity at constant volume, P2 V2 divided by R, minus P1 V1 divided by R. This is equation number 15. Rearrange the above equation. Finally, we get W is equal to minus CV divided by R, P2 V2 minus P1 V1. That is delta PV. Let us consider R divided by CV is equal to Cp minus Cv divided by Cv. This is only the mathematical simplification of the above equation. Finally, we get the another meaning, simplified meaning for W. These are all the various meaning for W. Thank you very much for watching.